This is Algebra 2 with trig, 2A.2. We're going to analyze graphs of polynomial functions. First thing we're going to look at is a k-value. A k-value is going to be considered the zero of the function. The k-value is the value that is x minus k. It's the value that's inside the parentheses typically, and that's going to be a factor. The k-value is a solution of the polynomial equation f of x equals 0. And k is a real number, k comma 0, for an x-intercept of the polynomial function. So we can tell a lot by this value, and they're considering this to be the k-value. If the factor is linear, it is a single zero. That means all of these are considered linear. They have to the first power, so they're considered a single zero. It goes through that value of the graph evenly. The graph crosses the x-axis at that point. So this here, if we're looking for when this equals 0, when it's 0, we don't have to do any extra math. If you wanted to know when it was 5, then you'd have to multiply it all together, collect your like terms, and bring it all over. But when it's 0, we can just set it equal to 0. One of these factors has to be 0. And when we get that, we get a value of 2, so the graph has to cross at 2. The graph could be at -1, or the graph could be at -4. And what we're going to talk about later is knowing how the graph goes through. I just missed that one, but it goes right through it. Put arrows on the end. And that would be our graph. We can see that with a graphing calculator, if you like to do that. We have x minus 2 and x plus 1 and x plus 4. You see the graph is going to go up, come down, and go back up. We're not worried about how high and low that we go, but the graph is going through. It's called a single zero because the graph goes right through it, very linear-like. It's a single zero. If the factor is squared, here's our factor, it is squared, it's considered to be a double zero. The graph's going to intersect the x-axis at this point. So what happens, again, we do our 0. This guy gets written twice if you want to think about it like that. This gets written once. We have a 0 at x equals 2. We have another 0 at x equals 2. That's why it's considered to be a double zero, because the squared factor is going to have two values at that exact same location. And then we have -1. So we're going to cross at 2, and we're going to cross at -1. Notice that this graph here had 3 different zeros. This one only has 2 different zeros, but this is considered a double zero. So we're expecting the graph to come up, it's going to hit that, and it's going to bounce the other direction. It bounces if the factor is squared. It's going to bounce on the x-axis at the location that that factor is squared. We can check to see what that looks like. X minus 2 squared and x plus 1. It's going to go up, bounce right on it, and then go back up. It's bouncing right at 2. And then here, if the factor is cubed, it has a triple zero. So again, we set this equal to 0. We can write it 3 times if you like to do that. And each one is going to be 2. So it's going to cross at 2. This is called a triple zero. You have to account for 3 separate zeros. So that would be a triple zero. Let's see what that looks like in our calculator to see that I'm not crazy. We have x minus 2 cubed. That's how you'd have to write it. And you graph that, and it's going to come up, it wiggles through there, and continues on. So the more complex the equation is, the more movement you get in the graph. Here we have 3 different sets of parentheses. We're going to have 3 different intercepts. Here we have 2 different sets of parentheses. We're going to have 2 different x-intercepts. And here we have 3 of the same factor, really 1 set of parentheses. So you're going to have 1 intercept. Multiplicity refers to the number of times a zero's associated factor appears in the polynomial. What this is really pointing out is what happens at the x-intercept. All right, because this is an even degree, it's going to cross twice right here. It's written in here twice. These are all written in here 1 time, so it's going to go right through it. It crosses it. Here we touch it, and then we proceed back. So here we know that we have x equals negative 2 and x equals 1. Now, typically, a cubic equation, this would be squared, this would be to the first power, so that's a total of 3. It would come up, bounce, and go back through. That's what it would typically do. But because we have an extra negative, we will be dropping down, bouncing, and coming through. That's because the negative is going to make it reflect over the x-axis. The degree here would be odd. Yes, we know it's 3, but the key term is that it's odd. That means the odd degree is going to be going in opposite directions. The end behavior, as x approaches negative infinity, the function is going up. As we move to the left, the function is going up. As x approaches positive infinity, the function approaches negative infinity. As we move to the right, positive infinity, the graph begins to go down. Here we have an a value, We have our different zeros. This is going to produce a -2. This will produce a 1. This will produce a 3. So -2, 1, +3. This is a cubic. 3 different factors. When multiplied together, we would get x cubed. So we know that this is going to start down low, and it's going to proceed to end going in a positive direction because the a value is positive. Because it's odd, it's going to be going in opposite directions. The 0.25 just means it's not going to go up as high as usual. We're not worried about how high it goes up. We're just going upwards, and then we're going downwards, and then we're going upwards. Don't worry about the maximum and minimum amount. We'll discuss that later. We just want to be able to sketch a reasonable 11th grade level graph for this equation. This is still an odd degree, so the graph goes in opposite directions. As x approaches negative infinity, this function approaches negative infinity. And as x approaches positive infinity, this function, let's take a look, it's going up when we move to the right. Positive infinity is to the right, and the graph is going up. It's going to positive y values, positive infinity. We're going to sketch this. Here we have x equals -3, x equals 4, and we're going to have it twice because that is squared. So we have 2 factors for that. That's a double 0. I'm expecting to bounce. This is 1. So at -3, at +4, and at +1. Now this is the 4th degree. 1, 2, 3, because it's a double 0, 4. So this is an even degree. It has a positive leading coefficient, so I know it's going to be going in a positive direction. You know that for sure. Because it's even, I know that they're going to be going in the same direction. At -3, it goes right through it. At 4, it's going to do the bouncing. So at 1, it goes through, and at 4, it bounces. Not concerned about how high you go or how low you go. Just get off the x-axis for sure. The end behavior, as x approaches negative infinity, our function, where's our function going when we look left? Negative infinity. When we go to the left, the graph is going up. And as we move to the right, to infinity, not just here where it's falling back down, but when we get far enough to the right where the graph has to be going up. We're going to talk about turning points. Here we're turning, and there we're turning. So many polynomial functions do not have a maximum or a minimum. This does have a minimum there, but some of our other graphs on the other side, this did not have a minimum because it went down forever, and it didn't have a maximum because it went up forever. So if it's an odd degree, it's not going to have a max or a min, but it can have what we call a local max or a local min. Okay, these y coordinates of the turning points of the function. The points that are maximum or minimum, then all the other values around them. This would be the lowest point in the neighborhood. and this will be the highest point in the neighborhood. Now, we still don't know exactly where it is. It most likely does not land right on integers. It does not land halfway in between. It's not on the line of symmetry. The graph of every polynomial function of degree n has n minus 1 turning points. A polynomial function has n distinct real zeros, then the graph has n minus 1 turning points. I'm sorry, this is n minus 1. The graph of every polynomial function of degree n, so like a cubic, it's going to have 3 minus 1. It's going to have 2 turning points, a maximum of 2 turning points. A polynomial function of n distinct zeros, it's going to have n minus 1. So here are 3 distinct zeros, and it has 2 turning points. 1, 2, 3. It has 3 turning points. This actually has a double zero here. So 1, 2, 3, 4. So we have 4 distinct zeros. This is going to have 3 turning points. Always 1 less than the degree. What is the maximum number of turning points? So here we see the number 5. So n minus 1 turning points. So 5 minus 1 equals 4 turning points. Next, we're going to look at a graph. We're going to look at the local maximum. That would be about here. What is the local maximum? 1, 2, 3, 4. It looks like a little bit more than 4. So 4.25. That would be the value of the local maximum. The value of the local minimum would be about negative 0.3 would be my guess. The zeros, this looks like negative 1.8. We have about 1 and about 1.8. So since this is going downwards and upwards, we know it's an odd degree. Because it has 2 turning points, it has 3 zeros, we would expect this to be a degree of 3. And if you look, it goes real smooth throughout this whole graph. It doesn't have any weird movements, so pretty confident that it would be made by a cubic equation. So these are 3 that you can try. You can pause the video. Give these 3 a try. Come on back and I'll talk you through it. Go ahead, pause it. We're going to create a polynomial function that has 3 x-intercepts with an n behavior that follows this pattern. Alright, has 3 x-intercepts. So x plus 2, x minus 1, and x minus 3. Those would be 3 x-intercepts. Now this says when we go to the left, the graph goes down. When we go to the right, the graph also goes down. Has 3 x-intercepts, but it's going in the same direction. So this must be an even degree. For one thing, for it to go down to the right, it has to be negative. But for it to go down in the same direction, it's got to be an even degree. This is an odd degree, so one of these has to be a double zero. So pick any of them. It's a double zero. Now what that graph might look like is x plus 2 could be out here. X minus 1 would be there. X minus 3 would be here. Because it's negative, it's falling to the right. I'm saying it's to the 4th degree because they're both going down. And we made the 3 the bouncer. It bounces right there. So that's what that graph might look like. But that's the equation. Your equation may have been different, but pretty similar to that. Did you have the negative? Did you have 3 separate factors? And was one of those factors doubled? It's the only way that you could get it to both go down. Write a polynomial function in standard form that has a maximum of 5 turning points. Alright, the standard form scares me, but it doesn't have to be exact. So we can just say x to the 5th, x to the 4th, x to the 3rd. Throw in some numbers if you want. 2x squared plus x minus 1. That's going to have a maximum of 5 turning points. Want to try it? Want to test it and find out what just happens? I made mine as pretty much as simple as you could. X to the 5th plus x to the 4th minus x to the 3rd plus 2x squared plus x minus 1. I'm betting you that this is going to cross 5 times. It might be a little crazy looking. Embarrassing. It didn't quite do exactly. Oh, my fault. Alright. The one reason why this wouldn't work, that makes sense now since I think about it. Okay. This would have a maximum of 5 turning points. That's why we say maximum here. If I would have made it with this, with actual factors, then it would have crossed 5 times. We just kind of threw in some terms. We threw in 5, 6 different terms. Therefore, that's might not calculate mathematically into 5 crosses. So this looks like a cubic, but it's actually the 5th degree. That's why this is a maximum of 5 turning points. It may not actually reach 5 turning points. What is the possible equation of this graph being shown? Well, this looks like it's crossing at x is a positive 1, so we have to say minus 1. It's bouncing there, so it's squared. Bouncing there, so it's squared. And it has to be going down, so it's going to be negative. We'll call this one g of x. Good job, everybody.